Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 9 on even and odd functions. So this should be a new topic for you, and let's jump right into it and talk a little bit about what even and odd functions are. Now, there are many different types of functions. One type that we've seen already are one-to-one functions. In this lesson, we'll look at two types of functions known as even and odd functions. And we'll see them right away in exercise 1. So let's take a look. Consider the basic quadratic and cubic functions f of x equals x squared and g of x equals x cubed. Letter A, evaluate the following without using your calculator. All right, now I've kept the numbers relatively low, relatively small, so what I'd like you to do is figure out what f of 3, g of 3, f of negative 3, and g of negative 3 are, given those two function definitions. Pause the video now and take a moment to do that. All right, let's go through it. At the board, f of 3 is going to be 3 squared, and of course 3 times 3 is 9, so f of 3 is 9. G of 3 is going to be 3 cubed, which of course I can think of as just being that 9 that I had in the last problem times 3 again, so that's going to be 27. F of negative 3 is going to be negative 3 squared, and a negative times a negative is a positive, so f of negative 3 is also 9. And then g of negative 3 is going to be negative 3 cubed, with a little red showing up just for good measure. And that's going to be that 9 that we just had times negative 3 again, so that's going to be negative 27. Let me just get that down. All right, great. So easy enough. I hope that was simple. I didn't have you doing like f and g of like 15 and negative 15. Let's take a look at letter B now. What do you notice above in terms of how the functions respond to opposite inputs? Inputs that have the same absolute value but have opposite signs. So I'd like you to just kind of take a look. I've got f of 3 and f of negative 3 versus g of 3 and g of negative 3. So think about that and see what you can state. Well, for f of x, which was x squared, opposite inputs of 3 and negative 3 resulted in equal outputs of 9 and positive 9. Positive 9 and positive 9. On the other hand, for g, right, opposite inputs of 3 and negative 3 ended up giving us opposite outputs of 27 and negative 27. So let's get that down. We don't have to write all of that down, but for f of x, opposite inputs gave equal outputs. I have to slow down on my writing. For g of x, opposite inputs gave opposite outputs. All right. Now, that was just for 3 and negative 3. Let's fill out a table to get a bigger picture here. So letter C. Fill out the following table for both functions. All right. Now, I think that you should probably be able to do this without a calculator, but if you need to use your calculator, go ahead. Again, we've got f of x equals x squared and g of x equals x cubed. We already know what the outputs are for negative 3 and positive 3. You just have to figure them out for negative 4, negative 2, negative 1, 0, 2, 1, 2, and 4. So pause the video now and go ahead and fill in that table. All right, well, the magic of the board here. So for f of x, right, when I have negative 4 and I square it, I get 16, negative 3, I get 9, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. And again, we see the same thing. Whether we have negative 4 or positive 4, the output is the same, right? Negative 3, positive 3, the output is the same. Negative 2, positive 2, the output is the same. So for f of x equals x squared, opposite inputs give us exactly the same outputs. Now for g of x, right? We see exactly the same trend again. Negative 4 gives me negative 64. Positive 4 gives me positive 64. Then we already had our negative 3 and 3 giving us negative 27 and positive 27. And negative 2 gives me negative 8, whereas positive 2 gives me positive 8. So for g of x, we see that opposite inputs give us opposite outputs. And that gets to the heart of what we call even and odd functions. So let's formally define them on the next slide. Here we go. Even and odd functions. Even and odd functions have a very strict algebraic definition. So let's bring that up to the top of the screen and then talk about it. Let's take a look. A function is known as even if f of negative x equals f of x for every value of x in the domain of f of x. Now, before we talk about odd, let's just make sure that we really kind of understand this, because sometimes it can be difficult to think about an algebraic definition. Basically, this is saying, look, it doesn't matter whether I have negative 5 and positive 5, negative 22 and positive 22. If I put an opposite output into f of x, I get exactly the same thing as an opposite input into f of x, I get exactly the same thing as if I put in the positive version, right? So opposite inputs give us equal outputs. Now let's talk about odd functions. A function is odd if f of negative x equals negative f of x for every value of x in the domain of f of x. So here, right, opposite inputs are giving us opposite outputs. All right. Now, it doesn't mean that a negative value of x will give you a negative value of y, and a positive value of x will give you a positive value of y, although that was the case in our first exercise. It just means that if I have an odd function, whatever the output is at negative 5 will be the opposite sign of whatever the output was at positive 5. So if at positive 5 the output was negative 10, then the output at negative 5 will be positive 10. Odd functions, opposite outputs for opposite inputs. So let's test this a little bit in exercise number 2. Consider the partial graph of the function f of x shown twice below. Sketch the other half of the function if in A, f of x is even, and in B, f of x is odd. The 3 coordinate pairs are listed to help you plot. Now, of course, there's lots of other coordinate pairs that exist on both of these two graphs, but I just kind of put down the 0, 0, 3, 5, and 6, negative 2. So let's go through this together and really talk about the idea. Now, 0, 0, that's kind of unique in that 0 is both its opposite, is its own opposite. So negative 0 is 0 itself. But if I look at the pair 3, 5, right, for an even function, what I know then is for negative 3, I should also have positive 5, because opposite inputs give me the same output. And for that coordinate pair 6, negative 2, if I put in negative 6, I also have to have negative 2, right? So as soon as I change the sign of the x's, the y's have to remain the same. Opposite inputs give me the same output for an even function. Now I can easily plot that, right? I can go to negative 3, positive 5. I can go to negative 6, negative 2. And I can draw that in, and I kind of get an M shape in this case. Now on the other hand, when I have an odd function, and I have the point 3, 5, then if I have an opposite input, I should get an opposite output. So negative 3 should get mapped to negative 5. Likewise, negative 6 now should get mapped to positive 2. I can plot those, negative 3, negative 5, and negative 6, positive 2, and I get kind of more of this zigzag-looking graph, right? And that's really the essence of even and odd functions. They don't really have so much to do with the formula for the function, if one even exists. It just has to do with how the function responds to opposite inputs. For an even function, right, when I have 3, 5, I'll also have negative 3, 5. On the other hand, for an odd function, when I have 3, 5, I'll then have negative 3, negative 5. And likewise with the 6, negative 2 point. So let's kind of keep going. Symmetry of even and odd functions. The graphs of all even and odd functions have specific geometric symmetry to them. All right, so like things that you studied last year in geometry. Exercise number 3. Looking back at the two graphs from exercise number 2, finish the two sentences below to describe the graphical symmetry of even and odd functions. All right, so I would like you to pause the video and take a shot at this yourself. I need you to dig out some geometric terminology, hopefully from last year, and describe to me what kind of symmetry this graph has and what kind of symmetry this graph has. Go ahead and pause the video now and see what you can say. All right, well, the easy one should be the even function, right? So even functions have symmetry across the y-axis. All right. In other words, right, I could flip this entire graph across the y-axis and it would get mapped to itself. It would land on itself. Or I could sort of like, let's say, fold the left half over and it would just land, or sorry, fold the right half over and it would just land on the left half. Odd functions are a little bit more difficult to describe, at least for me. Maybe they aren't for you. But these have what are called point symmetry across the origin. So odd functions have point symmetry across the origin. If you said that they have 180-degree rotational symmetry through the origin, that is also beautiful as well. In other words, if I took this graph and I rotated it 180 degrees around the origin, then it would look exactly the same. So this point rotated 180 degrees would land on that point, and this point rotated 180 degrees would land on that point. So it's got point symmetry across the origin or through the origin. And again, that one's a little bit more difficult to describe as opposed to sort of line symmetry where we just sort of like reflect something across the y-axis. And that will be true always for even and odd functions, because literally the definition of reflecting a point across the y-axis means that you switch the sign of the x-coordinate, but the y-coordinate stays the same. On the other hand, when you reflect a point through the origin or rotate it 180 degrees about the origin, what happens is both the x and the y coordinates change their sign. So 3, 5 becomes -3, -5. And 6, -2 becomes -6, +2. Hopefully a little bit of this sounds familiar from your geometry course. Let's keep going. Now, some functions are even, some functions are odd, and many functions, actually most functions, are neither even nor odd, right? That's just the way it is. Some functions are linear, some functions are quadratic, and a lot of functions aren't linear or quadratic. So let's take a look at a couple exercises and see if we can identify whether a function is even or odd. Exercise number 4. Consider the function f of x equals the absolute value of x minus 3. Letter A, test this function with a variety of opposite inputs to see if it appears even or odd. All right, so what I'd like you to do is just try that, right? So take something like x equals 2 and x equals -2. Evaluate both in this function and see what you get. Then maybe try it again with another couple inputs that are opposite of each other and see what you get. And then from that, try to get some kind of feeling whether it's even or odd or neither. Pause the video now and see what you can do. Well, I love myself some 1 and -1. Let's try that. So let's do f of 1. F of 1 will be the absolute value of 1 minus 3, which is 1 minus 3, which is -2. F of -1 will be the absolute value of -1 minus 3, which will be 1 minus 3, which is equal to -2. Now, if we've got just a simple choice, even or odd, then we already know the answer. These two opposite inputs gave us equal outputs, so it would have to be even. But let's do just one more set of opposite inputs. Let's do, why not? Let's say f of 5 and f of negative 5. F of 5, absolute value of 5, minus 3, which is 5 minus 3, and that's 2. Of course, I had to pick one that almost looked the same. And then f of negative 5, absolute value of negative 5, minus 3, 5 minus 3, and that's also 2. And that's starting to build up some really good evidence that this is an even function. Now, that being said, the reason, of course, that it's an even function is that really the important piece of this function, which is the absolute value of x, is sort of the textbook example of an even function, right? Because it takes a positive number and leaves it positive, and it takes the opposite of that number and makes it positive, right? So it's sort of almost forcing the function to be even. All right? So it seems like this function is even. Wow, that was kind of interesting. Now, let's take a look at part B of this problem. Sketch a graph of this function on the grid below to verify. Well, we can probably do this even without our calculator, all right? But what I'd like you to do is take your calculator, see if you can, if you need to, put this into your calculator and create a sketch of the graph here, right? You just need a few more points. We already have some points here at 1 and negative 1 and 5 and negative 5. You might want to figure out just what f of 0 is, and that probably would be enough to allow you to sketch it. Pause the video now and go ahead and do that. Well, just really quickly down here, let me figure out what f of 0 is. That's the absolute value of 0 minus 3, which is 0 minus 3, and that's negative 3. Obviously, f of negative 0 is also negative 3, but that's just because f of 0 and f of negative 0 are exactly the same thing. Anyhow, so we've got plenty of points now. If you absolutely have to, of course, you can bring your calculator out. That's no problem, right? We could put our function in. Let me just do that really quickly. So let me go here, grab absolute value, put absolute value of x in, minus 3, enter. There's my graph. If I really want to make it look very, very similar to what I've got on the grid, then I might want to change my window settings to negative 5, 5, keep going down, negative 5, and 5. Then I really kind of see what's on the graph grid. It's not great. Maybe I wanted to futz with this a little bit. But ultimately, right, I'm going to get a graph that looks something like that. And if we want a really accurate graph, of course, we can generate a really good table of values. But here's that negative 5, positive 2, positive 5, positive 2, right? As well, we've got our negative 1, negative 2, positive 1, negative 2, and our 0, negative 3. And what we again see is that beautiful, and let's make a little note underneath here, symmetry across the y-axis, right? We could literally take that graph, flip it across the y-axis, and it would get mapped onto itself. It would land on itself. All right, let's take a look at another exercise. Another function. Exercise number 5. Consider the cubic polynomial g of x equals x cubed minus 4x. Letter A, fill in the following table using your calculator. What type of function is this? Explain. Well, let's remember, and actually let's do this together. Let's review how we can generate a table on our graphing calculator. So I'm going to exit here really quickly, go back into my graphing calculator. I'm just going to modify this particular function, should be easy enough. Go in here, my function, I need to kind of pan up. Whoops, no, I don't want that. Went one too far. All right, my function is x cubed minus 4x, so x to the third minus 4x. Great, enter, there's my function. If I hit Control T, it will give me a table, right? And now I really want to work with that table. Oh, I don't want my table to scroll that quickly, but I need to fill in my table from negative 3 to positive 3. So we've got our values. We can fill in for negative 3, negative 15, for negative 2, 0, for negative 1, 3, 0, 0, etc. So what I'd like you to do now is pause the video and go ahead and fill in that table. Take a little moment to do that now. All right, let me just minimize this for the time being. Let's fill in the table. There we have it, right? I have my negative 15 for positive 3, 0, 3, 0, negative 3, 0, and 15. Notice, right, it asks us what type of function is this explain. When my input was negative 3, my output was negative 15. When my input was positive 3, my output was positive 15. Opposite inputs gave me opposite outputs. Now, it's not that helpful when I have outputs of 0. That's not great. But when I have an input of negative 1, my output was 3. And when I had an input of positive 1, my output was negative 3. Again, opposite inputs are giving me opposite outputs. So it appears that this is an odd function. In fact, let's write that down. This is an odd function because opposite inputs give opposite outputs. Okay. And we want to take a look at that symmetry piece on the graph as well. Let's take a look at letter B. Sketch a graph of g of x using your calculator and the window indicated. All right, so I've already kind of given you the window. We already have it in our calculator already, but what I'd like you to do is maybe adjust your window so x min is negative 4, x max is 4, y minimum is negative 15, and y maximum is 15, and go ahead and graph that function. Now, you don't have to make this thing perfect. Let me go back into my full screen. But when I do graph it, I get that particular graph. And again, you see that beautiful symmetry across the origin. In other words, rotate that thing 180 degrees with the center at the origin, and that graph is going to land on itself. So I'm going to just kind of note that. Symmetry across the origin, just to really emphasize that. They love asking that on state exams, right? If you've got an even function, an odd function, whatever it is, what kind of symmetry will it have? Even functions will have that symmetry across the y-axis. Odd functions will have that symmetry across the origin. On the homework, I'm going to ask you a little question about what kind of function might have symmetry across the x-axis, just to get you thinking a little bit. Anyway, let's wrap this up. Throughout this course, we're going to be talking about a variety of different types of functions. And as we mentioned in a previous lesson, right, we categorize functions because of shared characteristics, right? And many functions fall into multiple categories, like f of x equals x squared is a quadratic function, but it's also an even function, right? There are many quadratic functions that aren't even functions, even though they have an x squared in them. Now, even and odd functions are just one way that we classify functions, and they're a very special type, or two very special types. Even functions are functions where when you put in opposite inputs, you get exactly the same output, and due to that, they have symmetry across the y-axis. Odd functions, however, for opposite inputs have opposite outputs, and therefore have symmetry across the origin. We're going to be seeing even and odd functions as we move through this course, and of course, many examples of functions that are neither, such as exponential and logarithmic functions, which don't tend to be either even nor odd. All right, well, I want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.